Hello and namaste everyone. Welcome to lecture 11 of this NPTEL course on stochastic approximation. In the last week, we quickly skimmed over the basics of measure theoretic probability. In this week, we will now go a bit slowly and thoroughly understand the convergence of Martingale difference sequences by first understanding the convergence of a related stochastic process called as martingales. Alright, so to begin our study, we will need to understand this concept called as a filtration. So what is a filtration? Well, suppose we have been given a probability space omega, f and p. I hope with our introduction from the previous week, this notation should now be clear, but nevertheless let me give a quick recap of what the three things mean. This is your sample space, this is the sigma field of sets of subsets of omega, and this is the probability measure that is defined on calligraphic f, right. So given a probability space omega, f and p, a filtration is a sequence of sigma fields with the property that f0 is a subset of f1, f1 itself is a subset of f2 and so on and so forth, and every element in the sequence of sigma fields is a subset of f, right. So this is what is a filtration. So the filtration is basically the sequence fn, and henceforth we will refer to what is called as a filtered space when we have a probability space along with a filtration. So what is a filtered space? A filtered space is a probability space along with a filtration, and we will denote it in the following way with omega, f, fn and p, right. Okay. So now given a filtered space, we will now define what is called as an adapted process. Okay. So a sequence xn of random variables or equivalently a stochastic process is said to be adapted to a filtration fn if it satisfies the following properties, right, that xn belongs to fn, right. So again, when I write this notation, I do not mean that this belongs to is in the set notation context. What do I mean is that fn is a sigma field and xn is measurable with respect to fn, right, and recall that xn is basically a map from omega to r. So all xn's are defined on the same probability space and xn belongs to fn, which basically means that your xn inverse of b of r is a subset of fn, which itself is a subset of f. Okay. So this is what do I mean by an adapted process. Okay. Alright. So with this with these definitions in place, we can now define what is a martingale, right. So in our study of stochastic approximation, we would be requiring this concept of Martingale difference sequence. In order to understand a Martingale difference sequence, we will first understand this concept of a martingale, right. So for this we begin with a filtered space, and we will say a stochastic process xn is a martingale, right, relative to the given filtered space if it satisfies three properties. The first property that we require is that xn be adapted to this filtration fn. The next property we require is that all these xn's are integrable. In other words, we require that the expected value of absolute value of xn is less than infinity for all n. And lastly, and the most important property that we require is that the conditional expectation of xn plus 1 given fn is almost surely xn, that is on average xn plus 1 behaves like xn, right. And recall this conditional expectation notation, right. This at a very loose level is the best proxy for xn plus 1 that is measurable with respect to Fn. Okay. So, the conditional expectation is the best proxy for xn plus 1 that is measurable with respect to Fn, right, and we require that the best proxy for xn plus 1 that is measurable with respect to Fn be xn itself, and since we have presumed that xn is adapted to Fn, okay, this xn will indeed be measurable with respect to Fn, right. So, let us quickly recap what is a Martingale sequence. A Martingale is a stochastic process which has three properties. The first is that stochastic process is adapted to Fn. The next is that each element in this sequence is integrable, and the third is that the conditional expectation of xn plus 1 given Fn equals xn, and this property should hold for all n bigger than equal to 0. If all these properties hold, then we will refer to xn as a Martingale, right. Now, in similar spirit, we can define what is called as a Supermartingale or a Submartingale. In a Supermartingale, we again require that the first two properties hold. Instead of the third property, we require that xn satisfies this inequality. For a Martingale, recall that we had an equality over here. In Submartingale, we require that the equality be replaced by a less than equal to sign, right. So, what is a Supermartingale? A Supermartingale is a sequence xn which is adapted to Fn, is integrable, and its conditional expectation satisfies this inequality. In other words, on an average xn plus 1 is less than equal to xn. If the inequality is reversed, we have what is called as a Submartingale, right. So, in summary, a Martingale stays the same on an average, a Supermartingale decreases on an average, whereas a Submartingale increases. And in all these relations, you would have seen I have written almost sure here, and similarly I have written almost sure here, because as I told you, in the definition of the conditional expectation, if we change the definition of a random variable over a set of measure 0, then these definitions do not change. Hence, we only require that these relations hold except for a set of probability measure 0. Alright. So, I will soon be giving you some examples of Martingales, but before that let us make few points clear, right. So, it is obvious to see that a sequence xn is a Supermartingale if and only if minus xn is a Submartingale, right. So, it is easy to see that if a sequence xn satisfies this inequality, then if you take the negative of this sequence, then it will satisfy this inequality, that is the inequality would get reversed. Hence, if xn is a Supermartingale, then the negative of that process will be a Submartingale, right. Now, as I told you, in stochastic approximation, the stochastic process that would be of prime importance is not exactly the Martingale sequence, but rather it is the Martingale difference sequence. Okay. So, now let me quickly define what is a Martingale difference sequence, right. So, we begin with a Martingale sequence, and henceforth I will often denote a Martingale sequence in the following way, that is xn comma Fn. So, Fn is the filtration and xn is your stochastic process, right. So, given a Martingale sequence xn comma Fn, the sequence mn comma Fn given by mn plus 1 equals xn plus 1 minus xn, right. So, if you consider this process, then this process is what is referred to as the Martingale difference sequence, right. So, now I hope the name makes sense. Xn is your Martingale sequence, and now we are looking at the difference between successive elements of your Martingale sequence, and hence this new process is referred to as the Martingale difference sequence, right. Now, one can easily see that your Martingale difference sequence satisfies the following property. If you look at the conditional expectation of mn plus 1 with respect to the sigma field Fn, right, where Fn is, let us say the sigma field with respect to which your xn is adapted, right. So xn is adapted with respect to Fn, right. So this is the sigma field that is given to you, and let us look at the conditional expectation of Mn plus 1 with respect to this sigma field Fn, right. So from the definition of Mn plus 1 we know that Mn plus 1 equals xn plus 1 minus xn, hence this conditional expectation equals this conditional expectation. Now from the linearity of expectation, conditional expectation, sorry, this expectation equals the conditional expectation of xn plus 1 given Fn and the conditional expectation of xn given Fn. However, xn is measurable with respect to Fn, hence the conditional expectation of xn with respect to Fn is xn itself, right. Now from the Martingale property, the conditional expectation of xn plus 1 given Fn is xn, and from this we can see that we have xn minus xn which is 0, and I would like to again highlight that because we are working with conditional expectations, all these equalities actually only hold in an almost sure sense, right. So let us just summarize what we have seen, that if we have been given a Martingale sequence and if we look at the difference between the successive elements, then their conditional expectation of the successive differences, that is the conditional expectation of Mn plus 1 given Fn is 0 almost surely, right. So your Martingale difference sequence actually satisfies this special property, hence we can also come up with an alternative definition of a Martingale difference sequence which is given now. So given a filtered space omega f, sequence Fn and P, a sequence Mn is called a Martingale difference if it satisfies the following properties, that is Mn is adapted to Fn, right, or in other words for every n your Mn is measurable with respect to Fn. Furthermore, your Mn is integrable for every n, and importantly the conditional expectation of Mn plus 1 given Fn is 0 almost surely, right. And as an exercise I would encourage you to check whether a sequence of 0 mean independent and identically distributed random variables, if it is a Martingale difference sequence or not, okay. So now as promised we will look at some examples of Martingales, and once you see Martingales you can easily cook up examples of Martingale difference sequences, okay. The first of the examples that we will be looking at corresponds to sums of independent random variables, okay. So let us look at the example. Let us say we have been given a sequence xk of so I think correct this should be, so let xk be a sequence of integrable and independent random variables. So integrable means that your expected value of xk is less than infinity for all k bigger than equal to 1. Further, suppose that each of your xk's have 0 mean, right. Now with this definition of xk, let us cook up another sequence of random variables as follows. This new sequence is made up of your Sn random variables, and let S0 equal 0 and Sn equal the sum of the first n elements of this sequence xk, right. So now we have S0, S1, S2, S3 and so on. So we now have a sequence of random variables. Now the claim is that this new sequence is actually a Martingale sequence. Now as soon as I say that something is a Martingale sequence, the first thing that should arise in your mind is with respect to which filtration, okay. So let us answer that question, and towards that let us define the following filtration. So recall that a filtration is a sequence of sigma fields which are monotonically increasing. So the filtration that we work with is the one where the 0th sigma field is basically the trivial sigma field made up of only the empty set and the sample space, and for every n bigger than equal to 1 Fn equals the sigma field that is generated by the first n random variables, that is x1 to xn, right, and because x1 to xn are all measurable with respect to Fn and Sn is their sum, it is easy to see that Sn is measurable with respect to Fn, right. So, for those who are not able to see why that is the case, I encourage you to look at this textbook of random variables from this probability path by Resnick, alright. And then from some property that is satisfied by the expectation, which is referred to as the triangle inequality, one can show that the expected value of absolute value of Sn is upper bounded by the expected value of absolute value of k, where k goes from 1 to n. I think I made a mistake here, this should not be infinity, rather it should be n, okay. So, by one property satisfied by the expectation, one can see that the expected value of absolute value of Sn is upper bounded by the sum of expected value of absolute value of xk, where k ranges from 1 to n, and because each xk is integrable, each expectation is finite, and since this is a sum of finite elements, each of which is finite, the sum itself is finite. In other words, expected value of absolute value of Sn is less than infinity, and hence we can conclude that Sn itself is integrable for each n, right. So, we have now verified two of the three properties for when a sequence Sn can be claimed to be a Martingale sequence, right. So, we now move on to the third and final property, which is that of the conditional expectation of Sn plus 1 given Fn, right. So, again from the definition of Sn, one can express this Sn plus 1 as Sn plus xn plus 1, and now if you take its conditional expectation, right, from the linearity property, one can express this conditional expectation as the conditional expectation of Sn given Fn and the conditional expectation of xn plus 1 given Fn, right. Now, because Sn is measurable with respect to Fn, as we saw over here, this conditional expectation results in only Sn, and we rewrite this as above, right, and then we make use of the fact that xn is independent with respect to Fn, hence this quantity over here, okay, equals expected value of xn plus 1, and furthermore we know that each of these random variables has 0 mean, and hence this expression over here equals 0, and hence this whole expression equals Sn. And again I would like to highlight that all these four equalities actually hold only in an almost sure sense, right. So, what have we seen so far? That if I take the conditional expectation of Sn plus 1 given Fn, then it equals Sn, and from this we can conclude that Sn is actually a Martingale sequence, right. So, we see that the sum of independent 0 mean random variables actually forms a Martingale sequence. So, from this one may perhaps start believing that maybe to get a Martingale sequence we need this additive form, right, the additive form that we saw over here, right. So, using the next example I would like to show that no, that need not be the case, okay. So, the next example looks at products. In the first example we looked at sums, in the next example we are going to look at products of independent non-negative random variables with mean 1, okay. So, let us look at this example in more detail. Let us say we have a sequence of independent non-negative random variables with the property that expected value of xk equals 1 for all k bigger than equal to 1, right. So, with this property we are now going to construct a Martingale sequence in the following way. Let T0 equal 1 and Tn equal the product of the first n many elements, that is Tn equals x1 times x2 times x3 times all the way up till xn, right. And now the claim is that Tn is a Martingale sequence. Again one should ask with respect to which filtration. So let us construct that filtration. So let F0 be the trivial sigma field generated by the empty set and the sample space, and for every n bigger than equal to 1 let Fn be the sigma field generated by the first n elements of this sequence x1 to x1 x2 and so on. So the first n elements will comprise x1 x2 and so on all the way up till xn, right. And since Tn is a product of x1 to xn, again one can see easily that Tn is measurable with respect to Fn, right. So that sort of verifies the first property necessary for a sequence to be a Martingale sequence. The next property that we require is that Tn be integrable, right. So towards that let us look at the expected value of the absolute value of Tn, and since Tn is the product, this expectation equals the expected value of the product of x1 to xn, right, which in compact form I have written in the following way. And now we make use of the fact that each of these random variables, right, are independent, and because they are independent the expectation of the product becomes the product of expectations, and hence this thing equals this, right. And we know that each xk is integrable, hence expected value of absolute value of xk is less than infinity, and since it is a product of finitely many numbers, right, the product will also be less than infinity, allowing us to conclude that Tn is integrable, right. So this completes the verification of the second property of a Martingale sequence, and it now remains to verify the third property, which basically concerns the conditional expectation of Tn plus 1 given Fn. So let n greater than equal to 0 be arbitrary, and let us look at the conditional expectation of Tn plus 1 given Fn, right. And from the definition of Tn plus 1 we can break this into Tn times xn plus 1. Now the conditional expectation of this product equals Tn times this conditional expectation, and this happens because this Tn is measurable with respect to Fn, right. So I hope you recall the properties of conditional expectation which we had seen in the previous week, which we are invoking here to be able to write it in this fashion, right. And again from the independence of xn sequence one can see that this conditional expectation equals expectation of xn plus 1, and we know that each of these expectations equals 1, hence this quantity equals 1, and that is what I have written over here, and Tn times 1 is Tn itself. And again I would like to highlight that all of these equalities hold in an almost sure sense. Okay, so since we are dealing with such examples for the first time, and since we are going over these equalities for the first time, I am emphasizing this almost sure sense. So now let me summarize today's class. In today's class we looked at the definition of a Martingale, and we also looked at the definition of a Martingale sequence. Then we looked at two very simple examples of Martingales. In particular we looked at the sum of zero mean independent random variables, and we also looked at the product of independent random variables with unit mean, right. So the two examples were taken from standard textbooks, and their purpose was to illustrate that a Martingale sequence need not just be of the sum form, it can also have a product form, right. In the next class we will look at some additional properties of Martingales. With that, let me thank you for joining this lecture. Namaste.